So today we are going to start looking at section 4.2 in Algebra 2, which is talking about graphing rational functions. We did decide to do this as a one-day lesson because we are not going to get into the most complicated of situations in graphing rational functions. Having said that, this video might be slightly longer than a typical one. Because of that, we are going to skip our explore and reason today and jump into our first example. Before we really get into the highlight of what we're going to be talking about today, I'm going to show you one example of a different way to think about what we're going to be doing. This question asks me to rewrite g of x using long division. And then we're going to talk about how the quotient relates to the reciprocal function f of x equals 1 over x. So what this example allows us to do is to connect what we're going to do today to what we have been looking at in section 1. So if I take this rational expression, which we'll talk about what that means in just a second, and I do long division with it, saying put the x minus 3 out here and the 4x here. You could also do synthetic. The x goes into 4x 4 times. When I multiply it back out, I get 4x minus 12. Change my signs, and I get a remainder of 12. That means that we can rewrite this as 4 plus 12 over x minus 3. That goes back to last chapter about how you do long division and how you then can rewrite a remainder. Having said that, a lot of times we like to put that fraction first to compare it to 1 over x, so this would be the same as having 12 over x minus 3 plus 4. And again, this goes back to a little bit about what we talked about in section 1. We knew what the graph of 1 over x looked like. Okay, that's what we talked about. It was this graph. So if we know the shifts and what that does, we are able to find where those asymptotes move to. So first I see the x minus 3 on the bottom, which means that this graph goes 3 to the right, which means this vertical asymptote that was at x equals 0 moves to x equals 3. So I could go here and draw on my vertical asymptote. The next thing I see is this plus 4 on the right-hand side. The plus 4 would move the graph up 4. We talked in our video yesterday about how that affects the horizontal asymptote. So that would move my horizontal asymptote up to y equals 4. Last but not least, as a separate problem, we talked about how the number on top could affect the 1 over x graph. I think we did like 10 over x yesterday. What we learned is that it kind of stretches that graph away from the asymptotes. Now later today, we'll talk about how you can just plug in points, and we'll do that with the examples we're doing today. But as a general rule, we talked about in that last video how it pulls this part away from those asymptotes. Okay, so this is one option. You can take a rational expression, divide it out using long division to get it to show those translations that we learned about. Having said that, what we're going to learn today is that we could have probably gotten here just a little bit quicker, or at least without doing the long division, if we understand how to find the asymptotes in a different way. And that's what the main idea of today's lesson is. Before we get there, we want to get a couple of vocabulary words down. I've used them a couple times already, but if we say rational expression, we are talking about the ratio of two polynomials. So a polynomial divided by a polynomial. It becomes a rational function as soon as I set it equal to like an r of x or an f of x or a g of x or whatever. Okay, so make sure you understand when we're using these terms rational expression or rational function, you understand that we're really talking about when a polynomial is divided by a polynomial, because that's what we're going to work on graphing today. Now, as I talked about, in order to graph rational expressions, we need to be able to find where those asymptotes go. One strategy is to just do it algebraically, and that's what we're going to learn today. In order to do that, we need to understand that a vertical asymptote occurs when the x values are undefined. Okay, so if it's undefined somewhere, that is when where the vertical asymptote happens. Having said that, here's a key. If we're talking about a fraction, we know that fractions are undefined when the denominator is 0. That's important because with that example we just looked at, it started as g of x equals 4x over x minus 3. We're saying that the vertical asymptote happens when this fraction is undefined. Well, we know a fraction is undefined when the denominator equals 0. So if x minus 3 equals 0, then and the vertical asymptote is at x equals 3. Okay, so before I even did that long division, I could have just set the denominator equal to 0 and solved, and that would have told me the same thing we saw after the long division, which is that the vertical asymptote was over there. Okay? All right, so vertical asymptotes, you take the denominator, set them equal to 0, and solve for x. Sometimes it'll be a quadratic in the denominator, and you'll have to factor, but you still can set the denominator equal to 0 and solve for x. Horizontal asymptotes are a little trickier. When I say trickier, not necessarily harder, but trickier because we're going to have to remember 3 different cases. So you can see here, we're talking about how to find horizontal asymptotes. Now you might just want to follow along for a minute, and then in the end I will highlight what you might want to look at or what you might want to make sure you have written in your notes. This says that to identify horizontal asymptotes, compare the degree of the numerator to the degree of the denominator. Okay, so you might want to get that down now, I guess, before we start, and then you'll get your 3 cases down as we go. But here's the thing. If we're comparing the degree of a numerator to the degree of the denominator, we're talking about comparing 2 numbers. And if I compare 2 numbers, 3 different things can happen. The first one can be smaller than the second one. The first number can be bigger than the second number, or the 2 numbers can be equal. So when we say that we have to consider 3 cases, that's because we're comparing 2 different numbers, and there's 3 different ways that those can be compared. Now we must remember that the degree is the highest exponent. So when I look at this example, and this is where you don't necessarily have to write this down, but when I look at this example, the top is just x plus 4, which means x is my highest term. It has an exponent of 1, and the bottom has an x squared. So if I'm comparing the degree of the numerator to the degree of the denominator, I'm comparing a 1 to a 2, and the numerator is less than the denominator. Now, in order for us to truly understand what's happening, we are going to take these and plug in some values. If I plug in 1 on top and bottom, I'm left with 5 halves. If I plug in x equals 2, so I'm going to plug in x's that get bigger and bigger and bigger. Okay, so that gives me 6 on top over 5 on the bottom. If I plug in x equals 3, I end up with 7 over 10. If I plug in x equals 4, I get 8 over 17. What I can see that is as x gets bigger and bigger and bigger, the denominator gets bigger compared to the numerator, right? So my denominator is increasing, but my numerator is increasing as well, but slower. The numerator is going up by 1. The denominator is going up by 3, 5, 7, okay? What that means is this fraction is actually getting smaller and smaller and smaller and smaller. It's getting closer and closer to 0, okay? Because it's getting closer and closer to 0, it's never actually going to be 0. But that means that as x approaches infinity in this case, my y is approaching 0. And what that means, and this is what I need you to write down, is that the degree of the numerator, I think I added a word, when, I think I put when here, when the degree of the numerator is less than the degree of the denominator, there is a horizontal asymptote at y equals 0. Okay? All right, so that's the first case. Again, do you have to really know how to show all this work? Nope. You just need to see that as soon as the numerator, the degree of the numerator is smaller than the degree of the denominator, your horizontal asymptote is always going to be y equals 0. All right, that's the first case. Let's look at the second case. Second case is when the degree of the numerator is greater than the degree of the denominator. Okay, so you can see this flip. The x squared is on top, and it's an x to the first on the bottom. So the degree of the numerator is bigger than the degree of the denominator. Again, we're going to look at what happens as x gets bigger and bigger and bigger. So we're looking at as x goes to infinity, what's happening to my y's, or my h of x. So if I plug in 1 here, in this case, I get 2 over 3. If I plug in 2, I end up with 5 over 4. When I plug in 3, I get 10 over 5. I plug in 4, I get 17 over 7. These fractions keep getting bigger and bigger and bigger and bigger and bigger forever and ever and ever. And if something keeps getting bigger and bigger, we're saying that the y is going to infinity. And if it's going to infinity, that means that there is no horizontal asymptote. Okay, so when, back to our writing things out, we're going to write this out now in words. So the second case is when the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Now, just a quick side note, you don't need to know this for much in this class. When you get to pre-calc, you'll learn about it more. But if there's no horizontal asymptote, there is this thing called an oblique asymptote. Again, we don't do anything beyond that with it in this class, but I believe in one of your Pearson questions, it does just say, instead of there is no horizontal asymptote, it says there's an oblique asymptote. So these kind of mean the same thing, but we don't really need to understand what an oblique asymptote is. Really, it's a diagonal line that it approaches but never touches. But again, we won't be finding those in here, but when you get to pre-calc, you will. Okay, so when the degree on top is bigger than the degree on the bottom, there's no horizontal asymptote. And last but not least would be the case where the degree on top is equal to the degree on the bottom. Well, let's look at what happens. So if I go with what I did here before, I would get 3 over 0, which is undefined, so that's not helpful. So I plug in 2. So I'm plugging in as x's get bigger and bigger, gives me 11 thirds. Then I plug in 3, and I got 22 eighths. Plug in 4, and I get 37 over 15. Yep. Now, here's the hard part with this one. As I keep going with this, I'm not necessarily seeing as much of a pattern. I'm not getting closer to 0. I'm not getting bigger forever. So as a quick side note, I am going to do this problem with long division again, just to see what happens. Again, you do not need to know how to do long division for this chapter. This is just review. Okay, so if I do that, 2x squared divided by x is 2, so I get 2x squared minus 2, subtract, I get x plus 3. Okay, so when I have that, I can see that k of x in this case would equal 2 plus x plus 3 over x squared minus 1. And so in this case, as x gets bigger and bigger, so we already learned, now the degree of the numerator is less than the degree of the denominator. So this is going to become 0. So it approaches 2 plus 0. Now, again, you don't really need to know all of this with the long division, but what we can see is that that number on top, that's actually going to be the number that it approaches. So these numbers are actually getting closer and closer to 0, or to 2. So in this specific example, as x approaches infinity, my y approaches 2. But that's not always the case. It's not always going to approach 2, so let's compare it to the problem. Here is what happened. I compare those coefficients, right? Remember, I took this divided by this to figure out what number went up here. That was not a coincidence. The degree of the numerator, it is when the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the leading coefficients. So it's the leading coefficient of the numerator divided by the leading coefficient of the denominator. So that's the third scenario. Here's part of the horizontal. So I know that took a lot of time to go through, but learning those three different situations now makes it super quick and easy to find the horizontal asymptotes. So it takes a long time to introduce, but once you have them down, then it's easy to find. Now we can finally look at an example. So here's what the biggest thing you need to be able to do from this section is. Given a rational expression like this one here, f of x equals 3x minus 2 over x squared plus 7x plus 12, we are going to find the vertical asymptotes and the horizontal asymptotes. As a reminder, as it says here, the vertical asymptotes are when the denominator equals 0. My denominator is x squared plus 7x plus 12. I need to solve that for when it equals 0. I am once again going to use my factoring skills. Because a is 1, makes my job easy. Two numbers that multiply to 12 and add to 7, that's 3 and 4. So it factors as x plus 3 times x plus 4. Once I have it factored, I set each factor equal to 0. 4 equals 0. I solve. I get x equals negative 3, x equals negative 4. This situation actually has two vertical asymptotes. One at x equals negative 3, one at x equals negative 4. Now, horizontal asymptotes. We just spent a long time talking about all the different scenarios. I'm going to compare the degree of the numerator to the degree of the denominator. So in this case, my numerator, degree of my numerator, is a 1 because it's 3x to the first. My degree of the denominator is a 2 because it's x squared. Since 1 is less than 2, the degree of the numerator is less than the degree of the denominator. And if I go back to the slide where we talked about the degree of the numerator being less than the degree of the denominator, we said our horizontal asymptote is at y equals 0. So now because I know that information, I would just say my horizontal asymptote is at y equals 0 and I am done. Now, when it comes to things that are this complex, that have two vertical asymptotes, we are not going to graph those in this course. Again, we're going to leave that for pre-calculus. That's the piece we're skipping over. We're just going to do one vertical asymptote graphs, but we will ask you to find multiple vertical asymptotes. Okay, so you would just list it like this and you're done. Let's try another example. What are the vertical asymptotes and horizontal asymptotes of this function? Once again, I take the denominator, 3x squared minus 12, set it equal to 0 for my vertical asymptotes. Now in this case, I don't have to factor. There's only one term that has x's in it, so I can just solve. Okay. X squared equals 4. I do have to remember, though, that when I take the square root, I get two answers, plus or negative 2. So my vertical asymptotes are at x equals 2, x equals negative 2. Now, my horizontal asymptote. Again, I take the degree of the numerator. In this case, it's 2. Then I find the degree of my denominator, which is also 2. So that's when they're equal. That is when I take the ratio of the leading coefficients, which means I take the leading coefficient of numerator and divide it by the leading coefficient of the denominator. Again, the leading coefficient of the numerator, there's no number there, so it's a 1, which means it's a 1 on top. The leading coefficient of the denominator is a 3, 1 over 3. But remember, for a horizontal asymptote, you must write it as an equation. It's a horizontal line, so it's always y equals. It's y equals 1/3. All right, I want you to pause the video and try this one on your own. Okay, find the vertical and horizontal asymptotes. When you're done, unpause and check your answer. Hopefully for your vertical asymptotes, you found x equals 4 and x equals -2. You can see how I factored it if you missed that part. And then in this case, the degree of the numerator was equal to the degree of the denominator. So I took the ratio of the leading terms. So 2 went on top and 1 went on bottom. So my horizontal asymptote was at y equals 2. All right, I want you to practice one more on your own, but this one you're going to be like, why is it so much more simple or less complicated than the last one? And that's because we're going to use the more simplified one to talk about the ones you will have to be able to graph. So the ones we've just done, you'll have to be able to find vertical and horizontal asymptotes of these more complicated looking rational expressions. But if I was actually going to ask you to graph it, it would look more like this one. So I once again want you to pause the video and find the vertical and horizontal asymptotes of 2x plus 1 over 3x minus 4. Now, again, your work should have been a little bit simpler. You just had 3x minus 4 equal to 0 for your vertical asymptote. Add 4 divided by 3, so the vertical asymptote is at 4/3. The degree on top is equal to the degree on bottom, so I just took the ratio of the leading coefficients, so y equals 2/3. Now, the reason I had you use this is because if I give you this problem and ask you to graph it by hand, this is your first step. Find the vertical and the horizontal asymptote. So if we are going to graph a function of ax plus b over cx plus d, step 1 is to find the vertical asymptotes. Okay, so I would maybe write down these steps. So I would find the vertical asymptote, and then I would graph it. 4/3 is 1 1/3. I plot that there. Step 2 is to find the horizontal asymptote. Again, we just did that. At 2/3. Step 3 is to graph the rest of the function. Okay, I guess I drew these in as I was finding them. You could just wait till the end. But here's the last thing. We are going to choose a couple of x values on either side of the vertical asymptote to find the rest of the points. So if I wanted to find points on the left side here, I would pick like 0 and 1. I plug them into this. If I plug 0 in, I get 1 over -4, so -1/4 is a point. And then if I plug in 1, I got 5/2, which is 2.5. It should be -5/2. Oh no, I didn't plug in 1. That was the problem. When I plugged in 1, I got -3. Sorry, I was copying it from my notes. I looked at the wrong one. Plugged in 1, I got -3. That's sufficient, okay? So we know it travels kind of along those asymptotes. You always just want to find a couple of points, and really what those couple of points do is it just shows me kind of how far away it goes. That's why we're finding those points. Then I would find some on the other side, so I would pick like 2 and 3. Again, I plug it in for the x's here. When I plugged in 2, that's when I actually got 5/2, so 2.5. And when I plugged in 3, I got 7/2, which is 3.5. Oh, sorry, 7/5. See, I should just plug it in my head. So 1 and something. Okay, so it looks like this. Sorry about that. Try not to read my small handwriting when I'm doing this. Okay, so find your asymptotes, plot a couple of points, and you're good to go. Okay? All right, so let's look at a new example. Again, step 1 would find my vertical asymptotes. Take my denominator, set it equal to 0, and I solve. Again, I like to draw them in as I go. So I know there's a vertical asymptote here. Step 2, find the horizontal asymptote. The degree of the numerator equals the degree of the denominator, right? Because they're both 1. So I take the ratio. So y equals the top coefficient, the leading coefficient is 4. My bottom leading coefficient is 1. So there's a horizontal asymptote y equals 4. Last but not least, I want to check some points. I checked -10 first. When I checked -10, I got -43 over 2, which is -21.5. Okay, so it is way down here somewhere. So then I actually checked the other side. So I checked -7. When I plugged in -7, I got -31 over 1. When I plugged in 0, okay, so 0, I got -3/8, which would be right here. Okay, so we had gotten -7 was way down here. So it's going to look something like that. Okay, so I kept trying some points until I found some good ones. When I got, oh, so sorry, this was positive. That's where my problem was. -10, it was way up here somewhere. So again, it would just be out here somewhere. Okay, so again, sometimes if they're that big, it doesn't get as exact. But try to find a couple of nice points right nearby. This example that I'm going to have you try on your own is going to be a little bit simpler with that. So go ahead, pause the video, and let's finish up by you trying to graph this on your own. All right, let's see how you did. First of all, denominator x minus 1 equals 0 gives you a vertical asymptote at x equals 1. Horizontal asymptote, the coefficients was 3 over 1, so y equals 3. You can see my table here, or at least part of it. The bottom got kind of cut off. Sorry about that. With the table, I plugged in 2 and I got 8, so that was off the graph. 3, I got 11 halves. 4, though, I got 17 fourths, which is 4 1/4. So that's how I got that part of my curve. On the other side, 0, I got -2, -1, I got 1/2, and -2, I got 4/3. So that's where I got those 3 points. Okay, so if you had something like that, that was good. You would never have to find 6 full points. Usually 2 points or so, 1 to 2 per little curve is enough. All right, so like I said, I knew that video was going to get a little long, but now you have everything you need from section 4.2. So go ahead and start your Pearson practice, and tomorrow we'll move on to 4.3. Thank you.